So hello everyone, hope you are doing well and great. Today I am here to discuss about the algo which is used in every point of time in data science, whether it is a machine learning or deep learning. So when I started my journey in data science, I was not a person who belonged to maths background. I used to find it hard at my starting phase to understand the maths behind the algo of machine learning, but eventually I overcome all the challenges with a lot of practice and hard work. But I realized that this problem is not with me. It was with many of the budding data scientists who don't belong to maths background and struggle hard to understand the concept of the algorithm. And what I believe, data science is more about application of your knowledge rather than knowing your knowledge. And one of the algorithm which bugs a lot of budding data scientists is gradient descent. To understand this algorithm, maths alone cannot have a create a vivid memory of it. One need to have a clear image of its actual implementation. So the aim of this video is to enhance the conceptual clarity of gradient descent and understand the actual part of maths behind it. So today we are going to make our own gradient descent code from scratch and try to compare it with the inbuilt library of Python. So let's start. So guys, let's get started. So the first question, why gradient descent? So why gradient descent is because it is computationally less expensive than linear regression. Because in linear regression, we know the formula behind the linear regression is the ordinary least square method. So the time complexity of this regression is very high. It's around order of n cube. So it is computationally expensive. And we not only like I'm showing gradient descents in terms of linear regression. So gradient descent is also used in logistic regression and it can be used in any of the algorithm. The main purpose of gradient descent is to optimize the cost function. So whichever algorithm will be having the cost function, the gradient descent can be implemented. So that's the basic ideology behind knowing the gradient descent, because it is one of the algorithm which is used in so many of algorithms, whether it is machine learning or deep learning. So let's get started. So firstly, to like optimize the time, I've already imported the necessary libraries, and I have make my own data set with the help of this sklearn dot data set. My regression, you can make like with data set with any number of input features and with any number of output features. So I'm to just to make it simple, I'm just using one input feature and one output feature, because the idea behind making this video is to make the concept clear about the gradient descent. So let's get started. So we will start by splitting the data. So I have taken test size here. You can we can take the train size also. Like if I have taken the test size 0.2, it's mean like my 20% data will be going to the test and other 80% will be going into my training phase. So you can do vice versa as well. Okay, so like our splitting part is done. Now we are moving forward to initialize our module. Uh, so I'm like first I'm making the linear regression module so that like we can compare. We will be making our own code from scratch for the gradient descent, and we will compare our module with this linear regression in build library. Okay, so lr is equal to so okay, module lr dot So it's done. Now we can find the coefficient and the intercept line for this linear regression model. So the coefficient is 25 and this 2 is the intercept. So what this coefficient and intercept is, like the formula, as we know, the formula for the best fit line is y hat is equal to mx plus b. So this x is my like constant, I would say here, like it's x is my input feature and m is my slope and b is my intercept. So this is my intercept, this is my coefficient. I can say this can be weightage, can be said as weightage, slope, or the coefficient. Okay, so now we can also check the R2 score. Just okay to check the R2 score. R2 score. Y test. So we can see 0.639700 something is our R2 score. So guys, this part is done. We have built our module, LR module. So now let's move towards the making our own code from the scratch for the gradient descent. Okay, so let's start it. So guys, let's start with understanding the gradient descent. So this is my gradient descent, something. Bear with the drawing, please. Sorry, it was too bad. So this would be something my like gradient descent will be looking like. This is my y-axis, this is my x-axis, and the first thing what gradient descent do, it initialize the slope. Like the equation for the line is, we know the y hat is equal to y predict is equal to mx plus b. So my x is the future, m is the weightage or the coefficient of the slope, and b is the intercept, y intercept. Okay, so what gradient descent do first is randomly initialize any value for m and b. Okay, so suppose my gradient descent initialized from here, this is my b and this is my m. Suppose take b here. First I'm talking in terms of b. So there will be two things which I will be talking about while making the code. One is the epochs, one will be the epochs, and one will be the learning rate. So the epoch will be nothing but the steps that will be taken to reach the global minima. So as we all know, to in gradient descent, the major aim of this algorithm is to reach out the global minima to optimize, so that we can optimize the cost function. Okay, and the epochs, I told you, it is the iterations, it is the iterations that will be needed to reach to the global minima, and learning rate is the pace at which my each iteration will be moving. Okay, so like suppose this is my learning rate, and like my each, when I am just drawing this, it is my epoch, like my each step is epoch, and the pace which I am moving is the learning rate. So this thing I want to clear it first. Okay, so now I think we can start by building our own gradient descent class. So let's start it. So first I will do is I will make the class my gradient descent. Okay, so let me initialize something first. It will be self, comma, I need learning rate, and I need epochs, iterations. Okay, I need these two things. Self dot m. As I said, my m and b will be initialized randomly. It can be anything. It can be any value. Suppose I am taking m is equal to 100 and my self dot b is suppose minus 110. Okay, and I will tell you. I will visualize each and everything how it is working. I will tell each and everything in a very simple way so that the conceptual, as I promised, the conceptual clarity is the main idea behind this video. Okay, and self dot learning, it can be like lr is equal to learning rate, self dot box to box. Okay, so I have initialized the few things here. Now I will create some method. So as we know, in like in linear regression also we have two methods of fit and predict, so we will make that fit. We'll make the fit. For the time being, let's just let the pass and def dot predict. Okay, let's just pass. So now the things come. The fit. In fit, first I need to clear some few points. That is, the formula for the cost function or the loss function is summation of, we do summation of my actual y minus y hat. Okay, this is the formula for the loss function, and we take the square of it. Okay, and one more thing before going further, I want to make it clear, like why we are using mean square error and why not mean absolute error. Okay, so the first reason that we are using mean square error is like it will penalize the effect. What effect? It will penalize the effect if suppose my best fit line is drawn like this and my one of the data point is lying far away from it, so it will give more penalty to a data point which is far from it. So in this way it is penalizing the effect. So that's why we are using the mean square error. This is the first prior condition. And the second condition we can come to know that why we are using mean square error is because in gradient descent we know we have to find the global minima, and if suppose x modulus is a function of y, so a graph will be drawn like this. So sorry for the drawing. It will be drawn like this. So what will happen, this is a continuous, like this is a continuous function, but what is happening is it is not differentiable at 0 here. So we need a graph which is differentiable at 0. So that's why we use a square function so that it will be differentiable at 0 and we can find the global minima. Okay, so this was one of the point which I also want to make it clear. Usually we left this point. Okay, so thank you. So as you know, the equation for y hat is mx plus b. This is my equation. So instead of this y hat, can I write mx plus b? Okay, I can write here mx plus b. So so it can be written like this. Okay, return summation of y minus mx minus b. Okay, this square. So what I need to do, I need to do the differentiation of this b, like my my delta L by delta P. So in terms of B, if I'm differentiating this equation, so what I will get is I will get something like this. Just write it. So this 2 will come outside. Okay, and like B, this y will become 0 till mx will become 0 and b will become -1, and if when I will multiply this whole with -1, so -2 sign will come here. So by doing this, what I'm doing, I am calculating the slope, because I need to find out the amount of change in my x with each unit of change in my my amount of change in y in each unit of change in my x. Okay, so I'm calculating the slope for that. So I can write it like slope B can be written like this, minus 2 into and P dot summation, as we have to do the sigma function is here, summation y minus, so y hat can be written as self dot B into x dot rebel. So rebel I am using to just convert this x into 1D. Okay, this is the use of this. So y minus self dot b m into x, then minus self dot b. Okay, so this is done for calculating the slope of b. Now same can be done for calculating the slope of m. So this could be there. There will be only a one difference in calculating the slope of m. I will make it clear. Like at the end, our all of this equation will be multiplied by x dot well. Okay. So this will be the difference when you do the differentiation of sorry, this will be m cell dot m, m minus cell dot b in terms of m. Okay, so this will be the equation, right? Okay, so now what I can do now, so let me just show you one thing again. Let me just take back to this part here. So now what we have done, we have calculated the slope, but the major part which we are going to discuss, suppose like telling my code to reach to the global minima. I am a human, I have my eyes. By seeing this diagram, I can initialize that at this particular point my minima is there, but my code don't have eyes. Okay, so how we are going to guide him to reach to the global minima, that we are going to see now. Okay, so let's see this. So actually what we are going to do is like we are going to give eyes, we can say we are going to give eyes to our code. Okay, so we can say self dot b is equal to self dot b minus into, so the formula for calculating the like reaching to the new point is my old slope minus my new slope, like new slope, this can be considered as my new slope is equal to old minus the learning rate into old. Okay, the same can be done for the m part. So I will tell you what is happening. There is a very crucial catch here. So this is ready. We have given the eyes to our function. So how we have given the eyes to our like code, this minus sign is doing all the work. Now suppose I will show you it over here. Just let me share it again. Suppose this is my gradient descent. My b is somewhere here, and it is having a value of plus. It will be having a value of plus 100. Okay, so this plus 100 will be minus from learning rate into my 100. So what will happen? Suppose my learning rate is around whatever I give the learning rate can be x into my 100, so it will be x 100. So what will happen, this all equation will turn out into a minus sign. So when it turn out into a minus sign, it will become a I for it, because suppose this is my y-axis, this is my x-axis, this is my global minima. I am here in the plus right now. So what will have, like my next step will be in the minus direction, because my this all equation will turn into minus. My next move will become into the minus direction. The same will be case in here. Like suppose I am here, so like I having a minus 110 here. So what will happen, it will be minus 110 minus learning rate into my previous slope. So this minus and minus become plus, and we will start moving in the plus direction. So this is how we are showing our code, or we can say we are giving our code I, so that we can reach to a global minima. So let's code it. Okay, so work is done. We just need to print. We can print like coefficient here. Self dot b comma n. Okay, and this predict, now it is very easy. Just we have to return. We have to return what we have to return. We have to return the y hat. Y hat is nothing but self dot m into x dot given plus self dot b. This is my predict. So let me run it. Okay, it is giving me error. Name self is not defined. Oh, sorry, I have not defined it. Self comma, here my x will come, here my y will come, and self dot here my so I guess it's ready to go. Self is not defined. 15 20 self dot. So it is coming self. Okay, so this is the problem. I'm not using a for loop here because, as I said, we will be using epochs, the iterations to reach the global minima, and that was missing here. Okay. Sorry. Should working now. Just this. So our code is ready. Our own built-in code is ready for the gradient descent. Now we can initialize the things like GD is equal to my GD, and here I will pass the learning rate, comma 50. Okay. Now I will use the fit method here. GD dot my x train, comma x. Just comma y. So the coefficient value we are getting here is minus 72 and 60, but above we were getting 28 and 2. Now what's the problem? X train, Y train. Okay, this is the problem. Here we need to multiply with the slope we have calculated. Slope of p comma slope of m. Right. Now you can see we are getting exact coefficient and the intercept value is 28.1259. So with our linear regression model was giving 28.1259 and minus 2.27101 minus 27101. So exact, we are getting exact like what was required, and we can also check the R2 score here, like by P by predict. You can take the by predict equal to L my GD dot predict. Here I will take Y test, and we can calculate the R2 underscore on Y test, comma Y PD, or It's not defined. R2 score is not defined. What has happened? R2 score is not defined. Where it is gone? Done. Import. Now saying R2 score is not defined. It is not defined. I'm using the wrong spelling now. So you can see the R2 score also. R2 score is also the exact like 0.6345 what we get here, 0.6345. So what I need to say, like I can start at any random value. I can take it suppose 160 and 110, so it will work fine. It is going to give me the exact value of coefficient we are reaching to the global minima. So this was the coding part which I explained. Mentioned the crucial part here, like which is giving I to our gradient descent, is this minus sign. We are calculating the slope, we are giving the direction here, okay, and we are working here. So this was the coding part, like we have built our own class, we have understand how the things are working, how we have done the differentiation. So this is the actual math part. Like I have taken a very simple example of just one feature and one target feature. The it can be also done with the same for the more number of features. Okay, a little bit changes need to be there in the code, and same could be done. And this is the particular part where you need to understand the maths, the differentiation part, and rest is easy. Rest is nothing big, which I have done here. It's just normally I have calculated. I have just shown you the concept, like how we are moving towards the global minima, what is the concept behind it. So this is what I want to show you. And now comes the pictorization part, where I will be showing the animations, like how it is finding the best fit line. So stay tuned. So guys, as I mentioned, I will be showing you the pictorial presentation of gradient descent. What is going behind, how it is working. As I said, like understanding the math behind it doesn't give you a long memory or a vivid memory. So that it can last for a long time, we need to understand the gradient descent in a pictorial way, because it is the algorithm which is used in every part of like machine learning, deep learning. It is used in most of the algorithms. So like I have a pre-written code for showing you the animation part. For that, you can just have a look. So this is my data set. This is a scatter plot for my data set, like how my data is distributed. And after that, I will show you the how my gradient descent is finding the best fit line. So before coming towards it, I need to discuss one more thing. This B and M. So this B and M can also be said as the tuning parameter for my gradient descent. So what's the tuning parameter in terms of, like, if I change the value of B, if I increase the decrease of value of B, so what effect it is giving to my best fit line. So my best fit line will move upwards and downwards, okay, but it will not rotate over its axis. It will just move upwards and downwards if I change the value of B. But when I change the value of M, my best fit line axis is going to rotate. It is going to rotate over the axis. So that can be termed as the tuning parameter. So I will just show you how it's happening. So you can see I have just taken a random value of n and m, and with itself it is like, it is going to fit in the best fit format for this scatter data. Okay, so this is the beauty of the gradient descent. It ultimately find the best fit line. It reach to the global minima. Okay, so I can take any value. Suppose I have taken here 150 and 200. I can take here 150 and 160. So it will find it. So this is the beauty of the gradient descent. And of course, it is a fast algorithm. It have a less computational cost, so that's why it is being used. And most of the regression algorithms have this cost function. And gradient descents is also, many types of gradient descents are there, but I just want to give a basic conceptual clarity behind the gradient descent. Okay, and there is one more pictorial like presentation I need to show you. That is, you can understand this. So while by seeing this particular diagram, you can imagine like this is a x, like it is a function of x square, and you can imagine the graph is continuing like this side also. Just imagine this, and suppose this is my b and m. So you can see my, at the starting the pace is very high. Okay, the traveling pace of my learning rate is very high, but eventually it start decreasing when it find the global minima here. So by seeing this diagram, we can conclude one more thing. This learning rate, the value we are providing in the learning rate is very crucial and important. If we give a value very low, okay, so it will go to it will have to go to many iterations. Like suppose I will show you here, like this is my learning rate. If I increase the value, so what happened? Sorry, actually my graph will not be, my graph might not be fitting in it, so let me reduce it down. Okay, just take it one. Again having a problem. Okay, maybe it's not working, leave it. So you can just understand this, like if I increase the value of my LR, so what will happen, it will travel with a larger pace. And what will happen when it will travel to a larger phase, like first it will going here. If I take the value of, suppose if I take the value of my learning rate 100, so the next point after this might be around here and here. So it will not reach to the global minima. That's what I need to say. And I can also show you this. Just a second. It's not working here. I can show you. Yeah. So suppose this is my learning rate. This is my function. If I take this step, okay, if I take my step 0.001, so see how much steps I need to take to reach to the global minima. Okay, now it is traveling very slow, very slow, very slow. This is my global minima here. And suppose if I increase the learning rate, if I made it 3 or 0.04, now it will take a larger steps and eventually it will find the global minima. Okay, it will find the global minima. So but this, like previously we were using around 50 to 60 epochs is the times of iteration, but now it is done in 30. Suppose if I increase a little bit, like 20, so what will happen, it just take 4 iterations. Okay, so what will happen if I tremendously increase the amount of it to, suppose the maximum, I do it the maximum. Just a second, like suppose I do it, this is a very huge. Okay. See, my first, after my first iteration, the point is here. Okay, and what will happen in next, like here, what will happen next here? So what message it is giving to me, gradient descent will never reach the minimum loss, try again with the different learning rate. As my learning rate was very high, so it is traveling randomly to anywhere and it will not reach to the global minima. Okay, so this is the crucialness of the learning rate that we have to keep in mind. Okay, so that's it. I hope you enjoy, you liked it, and the aim of this video as was to make the concept clear behind the gradient descent. I have not talked about the maths part. There is a lot of maths part behind it. You will find it over the Google, and you can find it anywhere in the books. You can find it a lot of maths part, how it is getting calculated. But the conceptual part, like how it is happening, is this. Okay. So thank you. Goodbye.